This is the solution to problem 4-12 of Halliday, Resnick, and Walker. Let's go over and look at the problem itself. We're given some information about a bicyclist starting at a certain position. It says due east of a flagpole, and it got a velocity heading south. Then 30 seconds later, it says we're due north of the flagpole and going with a velocity east. So then we got some questions about displacements and average velocity and whatnot. But as I often do, let's sort of forget all of that stuff for a second and just talk about what this motion corresponds to. So, of course, first thing to do is to set up a coordinate system. So we can do that. We'll call the positive x direction the east and the positive y direction north. That's no reason not to do anything different. And then it says initially the bicyclist is off to the east. So let's put in that position vector and we'll call it R1. So that's where this bicyclist is to start off. And we also are told that the velocity is then heading south. Here with the velocity, we'll call it V1, headed directly south there. So, okay, that's the situation initially, and then 30 seconds later, we find out that the bicyclist is now sitting up here in the northern direction, the same distance, the same 40 meters, and the velocity is headed off to the right, to the east, like that. So when you read this problem initially, you might think, well, how does that happen? If we start out down here and we're heading south, how do we end up getting all the way up here? But of course, we're not given any information about what actually happens in between these two time periods. So all we know is the path starts off this direction, but then, you know, the bicyclist may do a little loop like that so that at 30 seconds, back up here at this position R2, or of course, you know, we don't really know anything about what might have gone on. It might have been all sorts of complicated stuff. All we know are the endpoints of that motion. All right, so then we can say, let's go and sort of figure out what we need to do in terms of answering the questions. So the first piece says, what's the magnitude and direction of the displacement? Okay, well, we know displacement is sort of the change in position from those two different values. So what we need to do is to evaluate delta R, we'll call it, as the difference between R2 and R1. So the easiest way to sort of do that is start with this R1 vector and turn it into its negative, which means have it go the other way, and then tack it up there on top of R2. So now we've got R2, and we're adding to it negative R1, and that's what we're calling delta R. So there it is, that vector displacement that heads over that direction. All right, now we need some actual numbers here. So how do we find the magnitude? Well, this is the Pythagorean theorem. It's the x component squared plus the y component squared. Those are at 90 degrees to each other. So that's the expression. In this case, both those distances are 40 meters, as I said before. So you probably know that just means when you sort of work it out that you can pull out a square root of 2 there. That becomes square root of 2 times 40 meters. And that then, if you put in your calculator, comes out to be 56.6 meters. The angle, again, this is pretty clear because it's a isosceles triangle, right triangle, and so as a consequence, I think most people realize that that's a 45-degree angle, and the way I've specified it here is 45 degrees west of north, meaning, remember, the way this works is you think about north, and then you rotate over 45 degrees to find the angle that corresponds to this particular displacement. Now, we know that Wiley Plus doesn't like that. Wiley Plus wants us to always do things relative to this positive x direction. So we have to think about how do you get to that displacement. You got to go all the way around over there, which means basically we just have another 90 degrees to add to this. And so Wiley Plus wants us to say it's 135 degrees counterclockwise from the positive x to x axis. All right, so that's fine. Let's just collect up all that stuff here, then the magnitude and the angle. And now let's go on and look at the next piece. The next piece says, okay, what about the magnitude and direction of the average velocity? Well, the average velocity is just well, we can write it out here. It's defined as being that displacement vector divided by the time that it takes to undergo that displacement. So there isn't really too much work to do here because we've got the magnitude of the displacement vector, the 56.1 meters, so we just divide by the time, the 30 seconds, And that gives us 1.89 meters per second is the average velocity. Remember, what we did is we went from here up to this point here, do it that way, and it took 30 seconds to do that. Well, of course, the angle again is the same as what we had before, the 45 degrees west of north. All right, so that's that. We're really moving along here. Collect up that information, and then we will do the last piece that says, okay, what about the magnitude and direction of the average acceleration? Well, average acceleration it's a similar kind of idea. It's the change in the velocity divided by the time. So we just do delta v divided by delta t, and we have to do a similar kind of thing here. The initial velocity, what I'm calling v1, starts off this way, and the final velocity is heading over that way. So how do we calculate that delta v? It's v2 minus v1, and we do the same thing we just did for the displacements, namely look at the negative v1, so watch this happen. We'll rotate it around to be minus v1, and then we'll just slide it on up there so that we've got v2 and then minus v1, and that means the difference in that, the delta v, is that vector connecting the two of them. So again, those two velocities are the same magnitude, so both 10 meters per second, so that comes out to be square root of 2 times 10 meters per second. The angle we can give here in terms of that, but it's a 45-degree angle again, or we can give it according to that as a 45-degree angle. So that's 45 degrees north of east, the way I described it here. And then the magnitude is 14.1 meters per second. So that gives us the change in the velocity, and now in order to calculate the acceleration, we need to put that into this expression here. Now you remember, I kind of don't like to do things in reverse order. If you do this, it's hard for me to recognize sort of how you sort of came up with that delta v, but I'm going to do it. So if you write something like this, it's always a good idea to do kind of what I did here to sort of show that this calculation you did subsequently is what goes up here into the numerator for this delta v. So some sort of an indication like that. Okay, but then 14.1 divided by 30 seconds is the 0.471 meters per second squared. And again, the angle of that we can give as 45 degrees north of east, which agrees with Wiley Plus's wishes there too, because that is relative to the positive x-axis. So I think that means we are done.